So Jarno will talk us about Lattice results for SU2 dark matter.
Alright, thanks. So continuing in the same theme, and I'm focusing on a smaller subsection of models today. So I think we are clear on the main motivations for this kind of study. Now, this actually, of course, this particular group of models arose from a Technicolor model in which someone pointed out that that you can actually have a dark matter candidate that would be interesting. Now, of course, you can have this model without the Technicolor parts, but it is, of course, one of the more interesting features of many of these strongly interacting models is that they can arise in a sort of a natural way from something else. Okay. So I'm talking about SU2 with two flavors, also known around here as two-color QCD. And so this is a simple model. It's there's a relatively small number of parameters, but it has a sort of an interesting phenomenology. It's in many ways quite different from QCD, but again, in some ways quite similar. So you can use this to build several different kinds of models of dark matter. You can make a strongly interacting particle in which a model in which this is really not coupled to the standard model, at least through any other interaction, but you can produce the correct thermal, the correct relic density through just internal treated to interactions of the dark matter particle, which would in this case be the pions, sort of, in this model. What I will talk about is this more asymmetric dark matter model, which actually is the one that arises from the Technicolor version of this theory. And I will also talk about how everything will basically be applicable to a symmetric dark matter model. You just couple it to the standard model in a slightly different way. And then I just want to point out, because there is a very interesting possibility that in this SU2 model, these baryons and mesons might form bound states to these dark nuclei. And of course, this is interesting just in general from the point of view of strong interactions, and you might have these nuclei forming in a model different from QCD, which is of course interesting. But in this case, they might actually change your phenomenology slightly, because your dark matter particles might be going through nucleosynthesis. Okay. Like I said, one of these models arises from a Technicolor model, so if that is the case, then we of course fix a pi to be 256 GeV, so we fix the scale of the model. Otherwise, it becomes of course a tunable parameter, and then you can change the results. Okay, so this is of course the Lagrangian, two colors and two flavors. And because the gauge group is pseudo-real, you can rewrite the Lagrangian in this form, where you manifestly see that there is an SU4 symmetry, so there is an enhanced flavor symmetry. And when you break this flavor, when this flavor symmetry spontaneously breaks, you break the maximal diagonal subgroup of the symmetry group, which breaks the symmetry from SU4 to SU4, and this creates 5 Goldstein bosons. Okay. So this has been basically checked on the lattice. This is actually the way the symmetry breaks, and you get the usual 3 Goldstein bosons, but in addition you get these 2 Goldstein bosons that you can create with this operator, and these are essentially your baryons. They come with two particles or two antiparticles, depending on if you choose which one you choose. Now, these are actually the dark matter models now. So this is the Technicolor version, and this is another one, Ectocolor. Should have had the references here, but they are coming. Okay. But in the Technicolor version, you couple it the way you would expect. So you have a doublet with the up quark and the down quark, and that is coupled to the electroweak interaction. So it has it's a doublet, and it has no hypercharge. The right-handed ones are now these utilities from here, and they just get a hypercharge. Okay. The other version, the non-Technicolor, it's called Ectocolor, just gets a hypercharge. But of course, when you put this on the lattice and you study interaction with the standard model, they look basically exactly the same. So now you get these three, once you introduce these charges, you are breaking, of course, the break isospin. So you get these three things that I'm calling pions, which are Goldstone bosons. They are mesons, and they have electric charges. Okay. And now, if this is a dark matter model, these things will decay away. They will not be. They will essentially have no relative density. And then you have these two baryonic states, which actually have a baryon number, and they actually are not pseudoscalar, but they are Goldstone bosons, and they have no charges. They actually only couple to these Goldstone bosons, possibly some heavier states, of course, in the model. Okay, so the symmetric version, again, this is Ectocolor version, is a dark matter model like the usual one. You produce the relic density essentially by through the same mechanism you use to produce the dark matter particles, the standard model temperature, and then at some point it decouples depending, of course, on the strength of the interaction. And in this case, indirect detection mechanisms, everything we can essentially write is suppressed, which is unusual for this kind of model. And essentially this arises because, this happens because we are building this charge neutral baryon, and the strongest indirect detection channel that you find happens when these interact with these pions, which of course then interact with standard model. Okay. But there are possibly, at least when you write down this model, you would think that there might be some direct detection channels that you could use to constrict the model. Okay. The asymmetric one is very similar, of course, but now we require some baryogenesis process. I'm not really commenting much about this. You could do the exercise with the production in the non-zero temperature transition, but we haven't done that. It would be some work. And of course, any phenomenologists will argue that there is asymmetry in the standard model, so you don't really know what produces that, so you don't know what produces this one. There are no indirect detection signals to speak of. There are, again, the same possible direct detection signals that people have looked at on the lattice. And the mass actually for the standard model particles would come from corrections that come from coupling this model to standard models. We know the scale, we have some estimates for these masses, but they are relatively difficult, of course, to put on the lattice. Okay, thanks. Now, the direct detection channels, which is really the only thing we have left because we have constructed the model so that it's very hard to see. There is, in the asymmetric one also, there is no set exchange. Of course, the symmetric one doesn't even couple to the weak interaction. There is a Higgs exchange in the asymmetric model because it is essentially constructed as a technical model. There could be a Higgs exchange also in the asymmetric one if the mass comes from a power coupling. If it doesn't, then there is no Higgs exchange in that model. Okay. Now, the charge radius is also 0 if you have the Play symmetry. If you have the action I just wrote down. If you break the Play symmetry, then you can have a charge radius, and we can actually estimate the strength of that. So, and of course, then you have polarizability, which you can estimate from chi-pt, but really you should calculate from the lattice. All right. So just quickly, you might have an interaction through the electromagnetic form factor if you break isospin. So if you have different masses for the different particles, and this essentially happens through these pion fields if you build a chi-pt version of this. So, but on the lattice, we just essentially couple the particles to an electromagnetic current. Now, on the lattice, we of course don't have isospin breaking. We are not putting it in. So, what we do is we calculate the electromagnetic form factor for the pions, and well, actually, they calculate it in this. So this is just Ari and Randy Lewis and Francesco. Okay. So what they did is calculate these form factors, and just notice that it fits pretty well to what you get if you assume vector meson dominance, which works in QCD. It's sort of a large N idea, so there's no reason really to expect it to work, but it seems to work. That's an interesting result on its own. But if you assume that this works also with the isospin breaking, then you can estimate the charge radius for these particles. So what you have here is essentially a measure of the isospin breaking. This is the difference in the masses of the vector mesons. And now you have the Higgs exchange also, which you can get in the asymmetric model, in the technicolor model, and here we have really no information to go on. So we are just writing from chi-pt the lowest order operators where you have an interaction with the Higgs, and some couplings that you assume to be of order 1. Okay. You could, of course, calculate Higgs exchange on the lattice if you assume Yukawa interaction creating the mass for the standard model particles that we have not done. That would be an interesting thing to do. But here we are just assuming that all the mass comes from just a direct mass term in the model itself. Okay. These are all plots from 2014, but so this has come down, as you saw from George's talk, to somewhere around here. So you're actually starting to constrain some of the space in this model, but essentially you're just saying that it has to be relatively flavor symmetric. A difference of 0.1 between vector mesons is pretty big, so because the vector mesons would be around 2 TeV anyway, so it's a relatively large mass difference. But still, you're starting to constrain the model. Okay. Now the electric polarizability is slightly easier to directly measure on the lattice things, and it's something that actually arises that you cannot get rid of no matter what you do. Right? So just in chi-pt, these terms contribute to the polarizability. You can do the calculation. At 0 mass, you will get, or at small mass, you will get a relatively accurate result from chi-pt. So this should, of course, connect at small mass. What we do on the lattice is we put in an an classical electric background field, and we see how this shifts the mass. So you should have an effective term like this with the background field. There's some lattice specific detail, but essentially in the end you get some mass that, or a shift in the mass that goes like the electric field squared, field strength squared. And we implement this, and we have some measurements of the mass at a few different values of the electric field. Now, what we're trying to do here is to just study the dependence on the lattice spacing. It seems to be of order 50 to, let's say 50%, so that's not that bad in this case, because, well, there's another source of systematic error, which is comes from doing the fit to this quadratic form here. We also do a quartic fit, and you get a slightly different result. Altogether, errors might be of order 100%, which is fine, because this actually, okay, I don't have it quite there yet. This is an extremely small number. So this connects with chi-pt, where the chi-pt result would be even on this scale relatively small. But like we would actually expect, the polarizability increases rather quickly with the mass. These are now in units where we assume f-pi to be 250 GeV. Okay? If you make f-pi larger, you can make the polarizability smaller, essentially. Okay? And then you can calculate the per-nucleon rate for xenon. And this is what you get. So this is the reason, of course, where we don't care about 100% error. We are a few orders of magnitude below the neutrino background. This is unfortunately what we get from this calculation. There doesn't seem to be a way we can scale this model to be able to rule it out. At least we can constrain the plate symmetry breaking. Okay. One point though is that which I didn't mention. Thanks. So one important point is that we didn't really model either of these models quite exactly. So in the other one, we have the normal mass term, but we don't have the Yukawa interaction, which you might want to add in there. And that would be detectable. And of course, we can assume that there is no Yukawa interaction, and then it's not detectable. But in this case, okay, so this is again for f-pi is 250 GeV, and this dark matter candidate mass here actually comes from that same direct mass in the model, direct fermion mass. So the problem with that, of course, is that that's not where the dark matter mass comes from. It's essentially in the Technicolor we are assuming that the fermions are massless, and we should add a mass term that arises from these couplings to the standard model. So it should actually break this SU4 symmetry in a different way. In any case, it's quite a few orders of magnitude below. So this might be an interesting thing to check in the end, but it seems to be quite hard to detect this model. So that's more or less the message. Thanks for your attention.
Thank you. We have time for questions.
So when you measure these polarizabilities with the background field method, you're using Wilson fermions, is that right?
Yeah, that's right.
So what happens when you introduce an external field is that the kappa critical changes. So you will have a direct contamination from a change in the mass, and you need to get rid of that. So that's something we found out last year. So there's a proceedings about that. It just might be an additional effect which actually contaminates the whole measurement, so that these get out wrong. I mean, of course, it's getting more and more severe when you go to smaller masses. So
Yeah.
it might well be in a region where it's not that large, but just as a comment.
Yeah. Okay. Thanks. So that's something to check.
Further question, comment? No.
So, as you said, in direct detection experiments, this is another one of these models that's almost impossible to see. Have you thought about collider signatures? Yeah.
Yeah, I have thought about them. We don't have any direct calculations, but in the asymmetric version, if you assume that the dark matter is relatively light, you are in this 5 GeV range, I would expect that there would be some signature. And this is really something that is a part of the technical version of the model. So it's well, I mean, you have to go there and check how these are taken into account.
Yeah, when you get the dark matter particle that light, what are the pions? The mass of the pions in that version of the model?
The pions are massless.
Oh no, they're not even. So, but sorry, your dark matter, you have two. I guess in that model, your 3 pions got eaten. That's the Technicolor version. You have this one light dark matter particle. What's happened to the 5th Goldstone boson?
Oh, that's actually also. So that's the complex conjugate of the other one, the anti-radical of the other one.
So they're both at the same mass, and
yeah,
okay.
Yeah, they would be. Of course, you can also separate them, give them a different mass, but there's no real direct reason to do that.
Yeah, but if you wanted to then turn this into a model of light asymmetric dark matter, how do you? And so the pions don't get eaten. How do you get rid of them to avoid left constraints? Have you thought about that? Is there any way to easily generate a big hierarchy between, let's say, these 5 GeV baryons and a pion multiplet that's much higher?
I think you can write down a mass term like that, but really, in this, at least in this Excel version, I think they're just kept in more or less the same range. But okay, so for asymmetric one, if you want to make it light, then you have to do something. But I was about to say, for the heavy asymmetric version, there is of course there's no problem like that, but then of course you have to add some mass term by hand.
All right, let's thank Jarno again.